Hi everyone, I'm going to show you how to make this little flip book, also called a foldable, for finding limits analytically. And the first thing we're going to do is put it together. So they're kind of fun. What we're going to do is, you see this line in the middle? We're going to cut this paper in half. Now, I'm a little sad. Do you see it doesn't seem like it was copied perfectly square? So it might be a little crooked, but we could fix it. So you need scissors and a stapler. Do you have a stapler at home? If you don't have a stapler at home, you need to go to the dollar store and get yourself a stapler. You know, in college, there's no staplers like in classrooms. You have to have one in your backpack. Super nerd status. Okay, sorry, I'm supposed to be teaching you how to do this. So I cut that paper in half, and then I fold it over like this, so this is the title. All right. Then this we're supposed to fold. I wonder which way we're supposed to fold. I think we're supposed to fold on this line. Rationalizing the numerator like this. So you see how that basic rules is right above techniques, but let's make sure this is right. If that folded right, that would be really cool. Yeah, do you see how the bottom here got cut off a little bit? So I'm going to cheat it. I'm going to try and fold it more on that line. Okay. These aren't perfect, but they're fun. A little fun review. Now I'm going to trim this because I'd rather trim this and have more room where this is to show my work. And I don't like how crooked it is. Okay, this goes, the one we just folded goes inside this one, and it should go like that. Now, if it's really bothering you, you can do some trimming. Yeah. So if it's really bothering, you can trim it, make it a little bit more perfect. But no matter how I copy these, they're hard to get perfect. Like this, like this. All right, we hope we got all the examples in here. You can check it before you staple it, but I'm going to live dangerously and just staple it. So staple it very close to the edge. Very, very close. Okay, so here's our flip book, and then inside there's examples, and then there's practice. And I'm going to do the practice until we have time. So until time runs out, I'll do as many examples as I can. So finding limits analytically, flip book. And when we open this up, well, look at that. Do a little fold. We have our basic rules, and we have what happens when the limit goes to infinity. We have some special limits that we may or may not have seen in class. So these are things to study and to memorize. Isn't that awesome? Little study guide. And now we have some examples. So for each of these, there's an example here already done for us, and then we have one to practice. So the example here, if f is continuous at a, then the limit as x approaches a means you just plug in a. So that's always step one on limits. You can see how the 3 was just plugged in here if this is a continuous function. So the example here, this is a continuous function, nothing funny. So we're just going to plug in what x is equal to. So x is equal to 7. And what's 7 plus 2? 9. And we know the square root of 9 is 3. So 3 minus 2 equals 1. Now I missed an equal sign. Let's see, if I put it here, then this equals this line of math, and if I put it here, that will equal this line of math. All right, there's our first example. Now, what happens if you plug it in and you get 0 over 0? Here we have a rational function with a common factor in the numerator and the denominator. So if you get a 0 in the denominator, you need to factor to see if something cancels or divides out. And that's what happened here in the example. Once it divides out, you plug in the number into whatever was left over, and there you get a whole. So in the example here, there is a whole when x equals 3 and the y value is 1/3, because 3 is the factor that canceled, and when you plugged the 3 in, we got a y value of negative 1/3. I don't know if I said that right. It's been a long day. Okay, so we're going to factor. It looks like this one we might run out of room. We're going to try our best. So x, what multiplies to get x squared? X times x. What multiplies to get negative 22? That would be 11 and 2. And those add to get 9 if the 11 is positive and the 2 is negative. in the denominator, we have a difference of 2 squares. Like that. All right, do we have a common factor? Yes, so the x minus 2 is common. And we're going to cross that off. And I'm probably going to save some room here. So once we cross that off, I don't have room to rewrite all this. Let's plug in the 2 to what's left over. So when you plug in 2 for x, we're going to get 2 plus 11 all over 2 plus 2. 2 plus 11 is 13 today, and over 2 plus 2, which is 4. Yeah? Good? Okay, so plug in. If you get a 0, factor and cancel, and we're on to number 3. So number 3 is new this year. It's kind of fun. Rationalizing the numerator. So if you plug in 16, we get 16 minus 16, which is 0, and that's bad. But you can't factor anything. So we're going to rationalize the numerator. And what that means is you're going to multiply the top and bottom by the conjugate. Say conjugate. Announcements. Announcements ruin my videos. Okay. So in the example here, this was square root x minus 2 times square root x plus 2. Okay. So we have square root x minus 4, so we're going to multiply by square root x plus 4. Okay, what this does every single time, it's going to create a difference of 2 squares, because we're going to have square root x times square root x. Hold on. Square root x times square root x is x, not x squared, just x. Square root x times 4 is 4 plus 4 square root x, and then minus 4 square root x, those cancel. Okay, the outside and the inside cancel, and then we have negative 4 times 4 is negative 16. You know, I thought I'll just whip out a new video this afternoon, but I think I'm tired and I'm kind of making silly mistakes. Don't distribute the denominator, leave those separate, but the numerator, the reason we multiply by the conjugate is we're going to get x minus 16. Okay, friends, what do you notice? Do you see x minus 16 over x minus 16? Yep. So what happens to us? They cancel? Oh, hey, what happens when everything cancels from the numerator? You get just a 1. So now we have the limit, as x approaches 16, of 1 over that. 1 over square root x plus 4. So now we can plug in 16, because we won't get a 0 in the denominator. How are we doing there? Square root of 16 is 4. 4 plus 4. Squeeze the answer in here. And how did I do on my equal signs? Not very good. The limit equals here, equals here. You can put it on either side, but there just should be 1 for each line. Okay, so in this little thing we have techniques if it's continuous and rational. So that's what this little tab is. So let's fold up this tab. Well, this looks like a lot of fun. More techniques, okay? So this is using conjugate for trig functions. You left your headphones. Hey, no problem. Thanks, you too. All right, so we have some trig functions here where we're going to use the trig identities that we learned in pre-calculus. Every time you see a 1 minus cosine or 1 minus sine or cosine minus 1, we're going to multiply by the conjugate. Sorry, I have trash in my hand. Multiply by the conjugate, just like we did that square root plus 1, square root plus 4, like that. So the example here says 1 minus cosine, and we multiplied by 1 plus cosine. We like this because we get 1 minus cosine squared, difference of 2 squares. And then we can change that out for a sine squared. So here we go. Ready? Cosine minus 1. So we're going to multiply by the conjugate, with it, which is cosine plus 1. Why is it called the conjugate? I don't know. It's kind of a mouthful. All it means is you got to make the difference of two squares yourself, okay? So what do you multiply by to make your own difference of two squares? The conjugate. It's going to be cosine squared minus 1 all over this mess. What do we have here? Sine times cosine x plus 1. All right, what does cosine squared minus 1 substitute out for? I don't know. Let me do some math here. Let's see. Sine squared plus cosine squared equals 1, but I have cosine squared minus 1. So if I were to subtract this 1, I would have cosine squared minus 1, but the sine squared, I'm going to move that to the other side. All right, let's clean up this mess. So cosine squared minus 1 actually equals negative sine squared. I don't know if you've ever seen that before. So we're going to substitute out cosine squared minus 1 substitutes out for negative sine squared. Negative, right? Now, we have a negative up there, but that's okay. We still have a sine squared over sine, so that will cancel out. One of these will cancel. Still have a negative. Don't lose that negative. But instead of sine squared, we just have sine now over cosine x plus 1. So what happened there? The sine squared, one of them canceled with this one. Okay, can we plug in 0? Well, what is the cosine at 0? The cosine, what's the x value at 0 degrees? The x value, if you have your little unit circle, the x value here at 0 is 1. So we can plug in 0. Here we go. Oops, what's the sine of 0? The sine of 0, what's the y value there? 0. Okay, what do we have here? We have negative 0 over 1 plus 1. What's 0 divided by 2 equals 0, and I'm out of room. There we go. There's 0. Ta-da. Multiplied by the conjugate. How are we doing on time? Oh my gosh, we might finish, yeah? Unless there's one on the back. Oh, there's one on the back. Okay, this, are you ready? We learned a way easier way. I don't want you to look at this, okay? This is like silly. I don't understand this. Anytime you have the same power over the same power, that's same over same, then the limit as x goes to infinity is called the horizontal asymptote, A-S-Y-M-P-T-O-T-E. And that is just the ratio of leading coefficients. Do you see that? So if you have, that only works for same over same. So do we have same over same here? But you have to look at the biggest one. You saw that's x5, and this is x5? Yep. So what's the ratio of leading coefficients? Negative 2 over 4, and this simplifies to negative 1/2. Remember, if you have small over big, like a small power over a bigger power, then the limit as x goes to infinity is 0. This is only for same power over same power. Yeah, forget that. Okay. And piecewise functions. How do you know if a limit exists for a piecewise function? You just plug in the x value into both pieces, and if they're equal, the limit exists, but if they're not equal, then the limit does not exist. So, ready? Here we go. We're going to substitute in negative 2 for here, and negative 2 squared is 4. We get 4 plus 5, and the lights went out. How are we doing? I know it's blue, but we're almost out of time. A few more seconds. 3 minus 3 times negative 2 equals 3 plus 6, which equals what? 9. So the limit of g as x approaches negative 2 equals 9. You did it. Okay, where do you put this? This is going to go in your little sheet protector. So for each unit, you should have a sheet protector where you can keep your flip books and then your quizzes. Your quizzes are going to go in here also. So this is Unit 1. Maybe you want to write on there Unit 1. And we'll do one more for Unit 1 next time. So I wrote Unit 1. Thanks for watching.